The next speaker of today is J Lawler, and he will talk to us about realizations of Unruh-DeWitt detectors in tabletop experiments. So please, Michael, the floor is yours.
Thank you. It's a pleasure to be here. I really think this RQI circuit is a wonderful way to build community, and I'm excited to be part of it. And I hope that through my talk that that we have a lot of questions in this area, and we're excited that there's such a large community of people who are interested in similar topics. So I will talk about realizations of Unruh-DeWitt detectors in condensed matter settings. That's what I mean by tabletop experiments. And we're interested in the question of whether we can make qubits talk to each other through electrons communicating between the qubits. And in order to help think about this problem, I've done some simulations. So the picture on the lower left is a picture from my simulation, and then the simulation takes place in one particular concrete setting, but I'll then branch out and talk about several other concrete settings. Then I will end with a discussion about what we're doing at Binghamton University as far as implementing some of these, or at least one of these settings, and that's I'll get to that. So several years ago at Binghamton, we were responding to one of the U.S. Department of Energy's solicitations. This one was on next generation quantum systems. And at Binghamton, some of us in the team were pretty good at making quantum dots, which could host a qubit, a spin qubit. So it's just a lump of material, and you put some spin impurities inside. It's a well-established technology. And we were wondering how we could use these quantum dots to build next-generation quantum systems. And we thought, what if we could exploit the fancy properties of topological materials in order to help these qubits communicate, in order to progress quantum information science. And topological materials, I'm not sure how many of you are familiar with them, they're fancy materials which have special properties that enable electrons to not scatter easily off of impurities. That you might normally give up the notion that electrons could be used in a material, could be used to help communicate quantum information because they just scatter a lot. That's what resistance is and resistivity is. But topological materials have a very special property that helps them avoid scattering off of these impurities. And so an example, the classic example is the quantum Hall effect, which is basically what we use. This effect is what we use to define resistance in a material. And here's an example where the Hall resistance is got a quantized value, but the longitudinal resistance is 0. So that 0 resistance is not scattering. Things are not scattering, and maybe we could use that effect to help qubits communicate in materials. And unfortunately, our proposal was not funded, but we wrote up a lot of our ideas in this paper, Design Constraints for Unruh-DeWitt Quantum Computers, which is on arXiv from last year. And it's in collaboration with a chemist, John Marone, who really helped us on the experimental side, and Eric Aspling, who's the next speaker in this sequence here. So you'll get to hear from Eric more about some of these things. I won't present everything. I won't present. Actually, what I'll do is I'll focus mostly on the experimental settings, and I'll leave more of the theoretical aspects to Eric's talk. So what we thought about, and this is something we could have actually grown at Binghamton University, is to grow a quantum well where we can trap electrons in a 2-dimensional layer. And we need a special quantum well. This mercury telluride, cadmium telluride quantum well, where these electrons have very special hopping properties so that they give us this topological material that I just mentioned. And it was first proposed that it would do this in 2006 in a paper by Bernavik, Hughes, and Zhang. And that was really the first, this material was actually the first topological insulator material. I don't know if you've heard of topological insulators, but it made a big splash back in 2006 that our theory of insulators was incomplete, and that there are two classes of insulators, the sort of trivial, topologically trivial, and topologically non-trivial. And this paper proposed the first real material to exhibit a topological insulating behavior. So here's my simulation. What I was able to do is I could basically create this image where every pixel in the image is an atom. And I take these rules for how these, and on each atom, I allow there to be, I think there's going to be, there ends up being 4 states. And for the electrons, the electron can take on 4 different states. Maybe you can think of it as 2 different orbitals on the atom. And then there are these, this model for how the electrons hop around in mercury telluride. And without turning on interaction, so free Fermi gas, I can simulate a very large system. 226 nanometers is the horizontal, and 130 nanometers is the vertical axis. And what I plotted here is the local density of states, which is just the projection or the wave function of the first 10 eigenstates summed over the sum of the first 10 eigenstates. And it just gives you a sense of where are the electrons in this low energy regime. And what happens is the electrons are not present in the bulk of the material, and they only live on the edge of the material. That's what I want to be, on the edge of the material. And in fact, we can even plot, here's like the wave function. It decays exponentially into the edge, and it has a fairly sharp intensity on the boundary. And now here's where maybe we started to get connected with Unruh-DeWitt detectors that, in one dimension, electrons obey the Dirac equation. So this boundary of this system, there are Dirac fermions that are going around the boundary. Actually, in these topological materials in general, those surface states are all Dirac fermions of one kind or another. Only here, the velocity of the Dirac fermions is not going to be speed of light. I'll come back to the velocity later. So it's a kind of emergent Dirac fermions. Although, of course, the electrons are ultimately Dirac fermions in the high energy scale. They become non-relativistic at low energies, and then they become relativistic again in the lowest energies in these materials. And so here's how we can actually build an Unruh-DeWitt detector, perhaps. What we can do is we can place that quantum dot right here on the edge of the system. And what I do is I turned on a magnetic field, and the color here is going to give the spin of the electron. So the fact that I'm plotting color shows that there's a spin qubit sitting here. And in the simulations, unfortunately, I did not treat the spin qubit as a quantum effect, a quantum qubit, but actually just basically it's just a static magnetic moment, because then at least I was at least it's efficient for the simulations. We hope to generalize to having a quantum qubits in the future sometime. So then what I can do is I can place an electric field over this region by putting down so-called top gate on the top. With top gate here is just a piece of metal you put on top of the system, and you apply a voltage to that metal, and it produces a magnetic electric field through that region. And Dirac fermions, though, it basically produces a potential barrier in this medium. And Dirac fermions would like to penetrate such barriers, but here I'm going to crank it up to 15 volts, and I sort of get out of this relativistic regime and back to a non-relativistic regime, so higher energies. And I can just so what happens is it just pushes the electrons around away from the edge. So now these electrons are flowing around the system, but now they see that they think the boundary of the system is this region here. And so I can use this play of the electrons to go back and forth between the having the gate present and not having the gate present. So, for example, so we have the we encode quantum information on the qubit, and then we can flash the coupling like that, and send it out into the field. That's the kind of basic idea, and then we can gain control over the our Unruh-DeWitt detector in a very detailed way. And ideally, what we would like to have is a very short time. If we have a very short time for this pulse, then this complex time evolution operator will become something simpler, just a more straightforward unitary operator. And that makes it easier for us to makes it easier to analyze the behavior of the system and figure out what should happen. And how do we know how short this time is? Our argument is really we want the time to be short on the scale of how, while we're turning on and off the qubit, the quantum information shouldn't spread very far from that qubit region. So, so if we put in some numbers, that distance there was about 100 nanometers. Then we can actually extract by studying the spectrum from the simulation. We can extract what the velocity is, and it turns out it's 0.5 times 10 to the 6 meters per second. So below the speed of light, but which on the scale of what we're talking about here, which is really millimeters per nanosecond or nanometers. Well, anyways, millimeters per nanosecond. It's or micrometers per nanosecond. It's 0.54 millimeters per nanosecond. And that converts to, you want to turn the gate on and off on a scale of 200 femtoseconds, which is extremely fast. Faster than any modern electronics can actually control. So we started, this is my next, I guess that's sort of the conclusion of this mercury telluride platform. So we started branching out, and we looked at graphene and the literature more, and we found there are actually a fairly long history in condensed matter physics of trying to get quantum information to propagate from a qubit to another qubit through a field. I mean, it's not a very big subject. Maybe it's not viewed as a particularly promising avenue, but nevertheless, it has been studied. And in 2007, there was an influential paper on graphene nanoribbons. Now, graphene is a two-dimensional carbon honeycomb lattice, and it is famous for being a condensed matter Dirac fermion system. Famous enough to win the Nobel Prize, kind of famous. And carbon can come in all kinds of different forms, and in this paper, they wrapped the sheet into a nanotube or nanoribbon, and created the following setting where you put a qubit on one side and a qubit on the other side, and you could get actually that these two qubits could talk to each other through the Dirac fermions propagating in the middle. So that's 2007. For this system, the speed of the Dirac fermions is well known, and maybe double what we had in the previous one. So it requires even a shorter gate. So that wasn't necessarily very helpful. We turned to other systems, and let me tell you about the one that turned out to be the most promising. These are this modern Moire pattern materials. I don't know if you've heard about these. There's been all the rage in strongly correlated electron systems and condensed matter physics. All we do is we have it's not graphene, but it's sort of like graphene. It's a transition metal diachel cogenides, TMD material, which is a honeycomb lattice with where the atoms are two different types of atoms. Like there's one layer here, it's kind of hard to see in this picture, but like one layer is red and blue, and the other one is green and orange. And when you have these two different atoms, then the Dirac fermions gain a mass. So it's massive Dirac fermions instead of massless Dirac fermions in the case of graphene. And what you can do is you can put two of these on top of each other. And because if you choose two different materials, here we had tungsten selenide and molybdenum telluride. Two different materials have two different lattice constants. And so by just placing two materials on top of each other, you get a different you get this huge moire pattern. And that moire pattern introduces a very long length scale in the problem. And that length scale changes all the time scales and everything that are necessary. And you end up with, we could go as high, we could get a switching time of 2 picoseconds, which is now getting into the realm of what electronics are possible, what's possible with electronics. Yeah, so I have other platforms I could tell you about, but let me mention now what we're actually doing at Binghamton, and this is happening in actually as we speak and into next semester. Largely, this effort is led by Eric Aspling. It's again in collaboration with John Marone, but we have several more team members at Binghamton, including Laura Elias, who is the grower who can grow these TMD materials, and Mengen Wen, who can study defects in these materials, and Zhong Lin is can study things optically and is a 2D material experimentalist. And what we're going to do is Anna's going to grow monolayers of tungsten sulfur, tungsten selenide. Actually, I don't know. There's several different options. I think it's tungsten sulfur. This paper I took this image from is tungsten sulfur 2. So it's one of these TMD materials. And just sprinkle it with vanadium defects. So we can control this at some level, the average separation between defects. So if we have a 0.4%, then you get a fairly large distance away between qubits. We claim now this is some of Mengen's work that these vanadium atoms are actually going to be qubits. We can use them to be qubits, and then we can control and look at different settings for different densities of qubits. These are not going to be nearly as impressive as Maxime's talk that had happened earlier, where he got very far with experimental realizations of Unruh-DeWitt detectors. But at the same time, it's a totally different platform. So, yeah. So we're hoping for that we could take it from this stage and go to this stage where we have a moire system down the road, and these moire systems are known to be able to host these topological materials, that kind of thing. So pull the story fully together. And so what we're going to get in the end is an experiment with Unruh-DeWitt detectors. And as far as I understand the state of theory of these things, that we really have only been studying a lot of models, and we're going to be faced with some experimental data, and that might have all kinds of complications that are real world complications. So we're maybe in great need of experts on modeling UdW detectors that could help us better understand what might happen in these experiments. And I guess lastly, I could just end with a comment, or am I out of time? Okay, right. Yeah. I just wanted to mention at the end that everything is relative, and in our system, the qubits are stationary in the Dirac fermions that are finite temperature T. And I wonder, if everything's relative, can we learn from the opposite case where the Dirac fermions are at zero temperature, but the qubits accelerate? So can that problem that is sort of extensively studied here in the RQI circuit, can we take information from that and help us figure out how to make these qubits nice qubits that don't talk to their environment? The central problem in quantum information science is qubits are always losing information to their environment. So yeah, I guess with that, let me end my talk. I could just throw my summary slide where we simulations, and yeah, I'll leave it at that. And I'm happy to take any questions.
Amazing. Thank you so much, Michael.